All right, let's look at the section 6.2. This section talks about the slightly more general principle of mathematical induction. All right, so let's look at that. All right, let's say m. M is just an integer, just any integer. All right, then you want to prove that for all n, starting from m, and m plus 1 and m plus 2 and so on, and the p of n is true. All right. So since it's starting from m, we shouldn't start from 1. So we should say, first thing you should do is we look at the p of m because this is the first one. Then we have to verify that this guy is true. Right? Then, as usual, we have to make sure that the two consecutive one, there's an implication. So for all k, starting from m, so m and m plus 1 and m plus 2 and so on, p of k, p of k implies p of k plus 1, right? Once you have those two things, then we can establish that for all integer n starting from m, p of n is true, right? So let's use that to prove this statement, right? So for integer greater than or equal to 5, 2 to the n is always strictly greater than n squared, right? So let's look at that. So try to prove by induction. So proof by induction. All right, so let's look at the base step, number 1. All right, base step would be, so starting from 5, so base step is, maybe I should say base step, right? That's n equals 5, right? So let's look at the 2 to the 5. So 2 to the 5th, right? 2 to the 5th is 32, right? We also look at 5 squared, right? So that's 25, right? So you can see that the 2 to the 5th is strictly greater than 5 squared, right? So that checks out the base step, right? Then number 2, induction hypothesis. So we assume that 2 to the k is greater than k squared, right? So this is induction hypothesis, right? We're assuming that when n equals k, then inequality holds, right? So third step, right? We have to look at 2 to the k plus 1. And we have to show that this is strictly greater than quantity k plus 1 squared, right? So first thing we do is, so k plus 1 power, so I'm going to pull out one of the 2. So this is same thing as 2 times 2 to the k, right? By induction hypothesis, we know that the 2 to the k is strictly greater than k squared. So this is going to be 2k squared, right? Then I'm going to split into 2k squared can be written as k squared plus k squared, right? But since k is greater than or equal to 5, I'm going to replace one of the k. So k squared, I keep the first k squared, but k squared is k times k, and I'm going to replace one of the k with 5. So it's 5k. Since k is greater than or equal to 5, we know that the k squared is greater than or equal to 5k, right? Then I'm going to use, let's say k squared is k squared. I'm going to split the 5k as 2k plus 3k, right? Then we know that I like the first two terms, so I'll keep k squared and the 2k, right? And we know that the 3k is definitely bigger than 1. Actually, this is strict inequality, so bigger than 1, so we can replace by 1, right? Which is exactly what we wanted, which is k, quantity k plus 1 squared, right? So we could show that 2k plus 1 is strictly greater than quantity k plus 1 squared. So this will checks out. So this is induction step when n equals k plus 1, right? And the last step is just a conclusion. So therefore, right, for all n, integer n, starting from 5 2 to the n is strictly greater than n squared. All right, that's it. I hope that this was clear.